All right, so today we're going to be looking at acids and bases, and this is just going to be a bunch of general properties over them, kind of a bunch of some random information in there, um, but all of it related and close together. All right, so first off, just some general properties. So for acids, they typically tend to taste sour. They'll turn litmus paper red, and they react with metals to form hydrogen gas. So a few ways to remember those. So first of all, the taste sour. If you think about things that taste sour, that's going to be a lot of fruits, things like oranges, lemons, stuff like that. And the thing that makes them sour is they have a lot of citric acid. You've probably heard of that before. It's what's in citrus fruits that, that's what gives them that sour taste. So acids are going to taste sour. Turning litmus paper red. We'll talk a little bit more about litmus paper at the end, but basically it's a slip of paper, and depending on whether it's an acid or a base, it'll turn red or blue. And it'll, if you move it from one to the other, it'll actually change to that color, even though it's already been used up once before. So I remember that litmus paper turns red in an acid because whenever I think of an acid, I usually think of the villain in a comic or something like that, where they have this big vat of acid, and Batman's hanging from above or whatever, getting slowly lowered into the vat because villains are dumb and don't just drop the hero in and immediately be done with it. And then we normally associate evil or bad guys with the color red, so that's kind of how I remember that acids make litmus paper red, because of that connection there between villains. Otherwise, it's just something, to make a flashcard or just something to get into your head. Same sort of thing with reacts with metals to make H2 gas. So anytime, or most times, whenever you put a metal into an acid, if the acid is strong enough, it'll react with that metal and you'll wind up making hydrogen gas off of it. All right, then bases are going to taste bitter. They feel slippery and they turn litmus paper blue. So this is where, I know that some of you this isn't a real common thing anymore, but way back in the day, even before my time a bit, whenever you say a bad word, mom and dad put soap in your mouth and you have to sit there for a while. If you've ever seen A Christmas Story, that happens to Ralphie. And so the reason that they put soap in your mouth, well, it's to make you have a clean mouth. But it's also a punishment because it doesn't taste good because it's really, really bitter. So it's the absolute, basically nastiest stuff that you could get. So it's going to taste really bitter. And then again, it feels slippery. So soap is a base, so you could think of that. And then it turns litmus paper blue. I kind of remember this one because bases and blue both start with B's. But again, other than those weird kind of memory device things, just something to memorize if you need to. All right, so then there are two different definitions for acids and bases. We have Arrhenius definitions, and then the next slide will have Bronsted-Lowry. So the Arrhenius definition is probably the easiest one to come up with. It's also probably the least useful, so 50-50 there, or pros and cons. But so an Arrhenius acid means that it contains an H in the formula. And so by having that H in the formula, specifically in the front of the formula, whenever it gets dissolved in water, it's going to produce H plus ions, or positive hydrogen ions in there. So for example, hydrochloric acid, or HCl there, is going to dissociate into H plus and Cl minus. So because it has that H there in the formula, that is what makes it an Arrhenius acid. Then an Arrhenius base contains an OH in the formula. So it produces OH whenever it dissolves in water. So sodium hydroxide, or NaOH, when it dissolves, makes Na plus and OH minus. So the Arrhenius definitions for acids and bases are purely based on whether there's an H at the beginning or an OH at the end. Then we have Bronsted-Lowry definitions. So these are a little more difficult, but they're going to be more useful. So this is the one that's going to get used a little more often. So a Bronsted-Lowry acid is something that donates a proton, which is the same thing as an H plus ion, or a hydrogen ion. So in this example here, I've got HCl plus H2O makes Cl minus plus H3O plus. So to figure out who the acid is, I'm going to look, the Bronsted-Lowry acid, I'm going to look at who donates a proton. So starting with my reactants, so I've got HCl and H2O here. When I look on the other side, I need to look at who donated or who lost that hydrogen. And so HCl turned into Cl minus, so I can see that it lost the H. So that means that HCl is a Bronsted-Lowry acid because it donated that proton. It's also an Arrhenius acid because it starts with an H there. For Bronsted-Lowry base, that's going to be something that accepts a proton, so completely opposite. So NH3 plus H2O, so we get NH4 and then OH minus. So the NH3 here, I can see it gained a proton because it went from NH3 to NH4 plus. So it gained not only an H, but also that positive charge there. So that's what makes it the base. Whereas here, this H2O is going to be a Bronsted-Lowry acid because it started as H2O and ended in OH. The difference there is it lost an H and it lost a positive. So that means it lost a proton. Therefore, Bronsted-Lowry acid. Just as a side note, where we've got like this H3O plus up here, that's called hydronium. And it's basically just a water molecule with an extra H plus attached to it. Technically, all H pluses or all hydrogen ions aren't actually going to be hydrogen ions. They are hydronium. But as far as the math and stuff is concerned, it's a lot easier just to pretend that they're H pluses and things work out. So just as a heads up, if you ever see H3O plus, it's the technically correct, but essentially exactly the same as H plus, at least for our needs and our purposes. If you take AP Chem or college Chem, you'll need to start differentiating between them. But for our purposes, we don't care. H plus, H3O plus, go crazy making them the same. Just know that H3O plus is called hydronium. All right, then strong and weak. I know we talked about this a little bit, so I'll go through a little more quickly here. So strong acids and bases are going to dissociate completely in water. So that means every single molecule that gets dissolved is going to dissociate or break into those two parts. So HCl was one of those strong acids, so it'll break apart into H plus and Cl minus. NaOH is a strong base, so it completely breaks apart into Na plus and then OH minus. And you'll never see any of those atoms or those molecules still bonded together. They're either broken apart or they're just simply not dissolved. Because they completely break apart, we're going to have a higher concentration of ions or protons in there. Because whenever we dissolve it, literally every bit of it is going to break into an ion, so there's going to be more ions per amount of solvent or whatever, so we get higher concentrations. And that's shown with a solid arrow, just like we've done with chemical reactions. It's saying that whenever this thing gets dissolved, it entirely makes this other thing, and that's it. Weak acids and bases are not going to fully dissociate in water, so when we dissolve them, they're only going to somewhat break up, but we're going to have both the whole molecule and we're going to have just a little bit of it, of each part broken up too. That ratio will just depend on the thing, but it's usually stacked much more in favor of staying as a whole molecule. So because of that, we get lower concentrations of ions and protons because not all of it's turned into ions, so there's going to be less ions in there. And that's shown with an equilibrium arrow, which is where you have two half arrows kind of stacked on top of each other. So any time you have a weak acid and base, we're going to use those equilibrium arrows. We're going to use those equilibrium arrows because it can actually go back and forth both ways. And we'll talk a little more about that here in a bit. All right. So, for this thing here, I want to know which one is an acid and which one is a base. So, based on both the Arrhenius and Bronsted-Lowry, see if you can figure that out. Just as a hint, only one of them is going to be able to work. So, go ahead and pause. Alright, so, for here, so I need to look at, first off, if I just use the Arrhenius definition, I need to figure out who has H in it. Well, both of these have H, so that's not going to work for the acid. And then figure out who has an OH there. And while it's kind of an H2O, it's not quite set up. So the Arrhenius definition of just simply looking for an H and then an OH is not going to work here. So we have to use the Bronsted-Lowry. And remember, this is going to be the more useful one. So starting with H2O, I need to look at what it turned into. So whether it turned into OH minus or NH4 plus. If think most of us can probably tell it's OH minus because, those are definitely more similar than H2O and NH4. So we have to figure out what happened between it on each side. So the differences are going to be, one, that there's less H there, and it also became negative, which means that it lost a positive. So since H2O lost an H plus, or lost that proton, H2O is going to be our acid. Whereas NH3 is going to be base by default, because if one of them is an acid, the other has to be the base. But we can double check to make sure we didn't do something dumb with the acid. So NH3 definitely turned into NH4. Difference there, it gained a plus, or it gained an H plus. And remember, anything that gains a proton or gains the H plus is a Bronsted-Lowry base. So in this case, water is going to be the acid, and then NH3 is going to be the base. So again, those Arrhenius definitions aren't always going to be the best, because it's really only better than Bronsted-Lowry if you're just like looking at formulas. If you're looking at an actual reaction, though, that Bronsted-Lowry is going to be definitely more useful. Okay, so those reverse reactions. So since there's a lot of ions in the water, and they're all floating around like crazy, some of them are going to try to react with one another. Specifically for those weak ones where you have equilibrium arrows. By the way, this is another way to draw those equilibrium arrows. Instead of doing the two halves on each other, you can also do like a full arrow, just with arrows on both ends of the line. So this allows the reaction to work backwards as well as forwards. So you wind up with a balance going on. And that's why it's called an equilibrium arrow, because everything will eventually settle into like equilibrium, where it's just going back and forth at the same rate. But anyway, so because it can go both backwards and forwards, we wind up with what are called conjugate acids and conjugate bases. So going forward, that last example that we just did, H2O and then NH3, we found that H2O was our acid because it donated the proton, and then NH3 was our base because it accepted it. But if this goes backwards, if it goes, instead of going from left to right, if it decides to go from right to left, now if I look, OH minus is going to turn into H2O. That means that it gained a proton, so it's a base, and that NH4 plus lost a hydrogen to turn into NH3, so that is going to be the conjugate acid. So the acid and the base are the things that are on the left side, or the reactions, or what we would typically think of as being what participates in the reaction. And the conjugate bases and acids are going to be the things that, if the reaction goes backwards, those are going to be those acids and bases. So whenever we look at those conjugate acids and bases, they always are going to occur in pairs, where whatever was my acid to begin with will be the conjugate base on the other side. Because if it lost that hydrogen to begin with, the reverse of it would be it gaining it. So that's why it's going to flip sides. So whatever's the acid becomes the conjugate base. And then that also means that whatever was the base is going to become the conjugate acid. Because base, remember, that means that it's gaining that proton. So then the opposite, or going backwards, is going to be that chemical losing that proton. And things that lose protons are bases. And so you can look at all these examples. But basically they're all going to follow that pattern. So HF turns into F, so I know that that's going to be the acid, and which then automatically makes that the conjugate base. And that makes sense, because if we go backwards, F turned into HF, that means that it had to gain a hydrogen, so that makes it the conjugate base. And so H2O, same sort of thing. We can tell it gains an H, so that makes it the base. And then the opposite is conjugate acid, and this is going to be conjugate acid because it's losing that H when it goes from H0 plus to H2O. So remember, acids and bases are always going to be on the reactant side. Conjugate acids and conjugate bases are always on what we consider to be the product side. And the conjugate acids, conjugate bases, those are for if it goes backwards. And then just as a heads up on this slide, all of the acids and bases and conjugate base and conjugate acids are all in the same place on each one. That is by no means a requirement. It's just to help you get the idea of, to make sure you know which one is the acid and base, and so on and so forth. So, like homework problems and stuff like that, chances are they're going to be all kinds of mixed up and stuff. All right, so go ahead and pause it real quick. But I want you to figure out who the acid, who the base, and conjugate acid and conjugate base are in each of these examples. Okay, so for the first one, so I'll start with trying to figure out who the acid is. So H2SO4 and H2O. So I need to look at who they turn into. H2SO4 turns into HSO4 1 minus. Definitely not H3O plus. So the difference here is that it lost a proton, so that makes this the acid. Then just because it's directly connected like that, that also means right off the bat that's going to be the conjugate base because those two are paired up. So it's got to be the opposite of whatever its other group member or its twin was. H2O, by process of elimination, we can tell that it's the base because one of them has to be an acid, the other has to be a base. But again, double check. It turned into H3O plus. That means it gained a proton or it gained that hydrogen. So it is going to be the base, which then makes that the conjugate acid. And we can double check that real quick. Going backwards, HSO4 minus gained a hydrogen, so it should be a base. But it's going to be the conjugate one because that's if it goes backwards. H3O plus, if we go backwards, loses a hydrogen, so conjugate acid. So for the next one, HCl turns into Cl negative, so it loses an H, which makes it an acid. Then that is going to be the conjugate base. Then that OH minus turns into H2O, so it gained a hydrogen, so that makes it a base, the opposite conjugate acid, and that's going to follow if we go backwards. H2O turns into OH, so it loses that H, which makes it an acid. Cl minus gains an H, which makes it a base. For this next one, I'm going to start with the base just because that's the color my marker's on right now. So HCl turns into Cl minus, so that's losing the H, so that's actually going to be the acid, which means that NH3 is the base. NH3 is also, we can tell, so first of all that it's paired with NH4, so it's definitely gaining that proton. But then that also means that this is the conjugate acid, because if we go backwards, it loses that H. Then HCl then, we said is the acid because it loses the H, also process of elimination there, which makes this the conjugate base. Again, process of elimination, it's grouped together, and Cl minus turns into HCl if it goes backward. So it gained an H, which makes it a base. All right, and then the last one. So H2O and then NH3. So H2O turns into OH minus, so it loses the hydrogen, so that's going to be the acid. That's conjugate base. Then the NH3 gains that hydrogen, so it's going to be the base. And then NH4 is the conjugate acid. And then, of course, it works the same backwards. So, again, this is just kind of a coincidence. On the left side, the acids were all written first, bases were all written second. That is not how it's always going to be. So just make sure you're on the lookout for that. And then on the product side, it did switch up, like especially on the second one here. So that order does not necessarily mean anything. But as we were looking through here, so we had water in two places. We had it up here at the top where it was a base, and then we had it down at the bottom where it's an acid. And so the reason for that is water is what's called amphoteric, which means that it can either be an acid or a base, just depending on the circumstances. Essentially, it's going to be whichever one is the opposite of what it's with. So if you put water into an acid, that water is going to act like a base. Or if you put water into a base, it's going to act like an acid. It's going to do the opposite of what it's in there, basically to allow the acid or base to either give away the protons or to take protons. But water, even with itself, because it is amphoteric, it's going to be able to be both a base and an acid. So H2O plus H2O can form both hydroxide and hydronium. And so this is happening with any water that is basically anywhere. So water in a water bottle, toilet, whatever, is all going through this. But it's such a crazy, intensely small amount because water would, or all of these atoms would very much prefer to be in water form. Those two water molecules then are going to have to hit together at the exactly right, basically every set of conditions for that one hydrogen to rip off of the one water molecule and to go on to the other to give that charge. But then they're basically immediately going to separate right off because water would rather be stable than be charged. But this does happen. But the important thing to remember is that water is amphoteric, so it can be an acid or a base. It just depends on the situation. So you've got to look at what it's with to figure out what it's going to be, which is what we did on the last slide here. On this one, water was with an acid, so that made it the base. Here, water was with a base, so that made it an acid. All right, then we've got the pH scale. So the pH scale is a numeric scale used to express the acidity of a solution, where pH stands for power of hydrogen. So it's basically telling you how acidic something is. It goes from 0 to 14, where 0 is going to be the absolute most acidic, and then 14 is going to be the least acidic, or consequently the most basic, since those are opposites. So anything with a pH of less than 7 is going to be considered an acid. Anything with a pH above 7 is going to be basic, and 7 is neutral. Where this comes from is basically just how logs work and stuff like that. But the bottom line is just remember that 7 is where those two things are going to split. Anything above it is a base, and anything below it is an acid. And this, again, is going to be another useful flashcard type thing, where you'll write, what is the pH, and then whether it's an acid, neutral, or base. So where this kind of comes into play, and you don't have to write these down by any means, is where we can look at kind of how acidic or how basic something is just simply by taking the pH. And there's some different ways to do that, which we'll talk about on the next slide. But it can tell you how acidic something is. So like if we go to the very top, we've got like battery acid. So if you've ever looked at the battery on your car, there's a big warning on there telling you not to open it because it has some really strong acid in there, like burn through your hand type acid strength. So you do not want to touch it because it's got to be strong for those chemical reactions that happen inside the battery so that you can start it and do all that stuff with your car. But because it has the lowest pH, that means it is the absolute strongest thing. Then we've got some other things on there. It starts to soften out a little bit at a pH of 2 with like lemon juice. If you've ever tried to drink straight lemon juice, it's not pleasant because it is really acidic. Same thing with vinegar. Vinegar also just tastes bad. But those two things are really going to make your mouth pucker up because they are pretty strong acids. They're not strong enough, of course, to eat away at anything unless you leave it sitting for a while. I would imagine that something like Coke or Pepsi, really any of the sodas, are somewhere in between these two things because they are really acidic. Like if you've ever, I think Mythbusters did a thing one time where they tested the acidity of soda by seeing what it did to teeth, and whether it was Pepper, Coke, whatever cola they were using, like ate through those very uncomfortably fast. So the lower the pH is, the stronger things are. Then we've got like acid rain, which is technically not as strong as orange juice is. But if you ever had like a cut on your lip or something like that and you've drank orange juice, it's not pleasant because you're basically just automatically adding an acid to your bloodstream. Your bloodstream doesn't like it. And so it's going to rebel. Whereas if you get like orange juice on your skin or even in your throat and stuff like that, the outside layer of basically every part of your body is made to protect you from a whole variety of things, including acids and bases. So even if it just touches it, it's going to be fine until it gets to some raw part of your skin. So like if you had like a cut on your lip or something like that, it's going to burn a whole lot more because of that. And then we get to pH of 7, that's pure water. That's really the only thing that's completely basic is going to be pure water. There are some things that you could put in water that would keep it basic because they're not going to be acids or bases. But you do essentially have to have pure water to have a base. Or to have a neutral substance, sorry. And then as we start going higher than 7, we start getting to basic stuff. So like baking soda here, so that's a base, because if you ever made a baking soda volcano, that's vinegar and baking soda put together. And so you wind up with all of those bubbles forming because there's that reaction between the acid and the base there. Milk of magnesia is basically Tums that your grandparents, maybe your parents, took way back in the day. You basically drink it if you had an upset stomach. And the reason that worked, because if you had an upset stomach, a lot of times that's because there's a lot of stomach acid buildup, especially like heartburn and things like that. So by drinking a base, or this milk of magnesia, that base cancels out with the acid, and so you wind up feeling better. That's how Tums work too. It's just a solid chunk of a base rather than liquid. Pepto-Bismol, same sort of way too. Then ammonia, so getting into cleaning solutions, for whatever reason, they're bases. I don't know why we use bases instead of acids, but we do. Soapy water, bleach is definitely very basic. And then liquid drain cleaner is going to be really basic. There's also an acidic drain cleaner too, but basically a whole big range of stuff there. All right, last bit. So indicators. So indicators are going to be a certain dye that turn different colors in solutions that have different pHs. And so there's a whole bunch of indicators. Just so you can kind of see over here, there's a whole bunch of them. The only 3 we care about, though, are going to be pH paper, phenolphthalein, that's how you pronounce that, phenolphthalein, and litmus paper. So pH paper is a variety of colors across the entire pH scale. If you have a pool, or you have a friend who has a pool, or if you work in a kitchen, a lot of times by the dishwasher, there will be a little vial of pH paper there too. But basically the way that works is you take the paper, you dip it in whatever the substance is, and then you compare it to a scale on the actual canister itself, and you just match up the color. So if it's green, it might be an acid, which means it has a pH of like 4. If it's a blue, then maybe it's a pH of 3 or something like that. But the paper is going to change color based on what the pH is. The nice thing about pH paper is that it doesn't have to be a very specific range. It can cover basically the whole spectrum, so you can get an idea of what it is, but it's not going to be super accurate. So you're not going to get a really close guesstimation. That's where all of these indicators over here come in, which includes phenolphthalein. Because if you look at these pH ranges, most of them are pretty small. They're within like 1 or 1.5 of each other. Some of them are a little bigger, but most of them are in that small range, and you can tell that there's a fairly easy distinguishable color change between them. So basically the way that these would work is if you're starting with your known sample of whatever it is, so maybe you're starting with an acid on bromocresol green, and it's a stronger one, and you need that solution to get to a pH of somewhere between these two, so let's say like 4.5 roughly. So you'd want to go until it's this color that's right between green and blue, and once you hit that area, you know that you've got it, and that's exactly the pH that you want. So that's how all these works, including phenolphthalein. So that's going to be pink in a base and clear in an acid. The curriculum does require that you actually know this, so that's, again, another flashcard thing. It's a great thing to write down on it. So you'll notice phenolphthalein isn't necessarily clear in an acid because it's 8.3 to 10. But whenever we start getting more into how the pH scale works later on, the difference between an 8 and then like a 7 is really not that much. They're actually really, really close together based on how the math works with logarithms and stuff. So for most purposes, it works fine. It's also easy to get a hold of. It's not carcinogenic or anything like that. So we tend to use it for a lot of stuff. But basically, it's pink in a base, clear in an acid. Then last is litmus paper. We already talked about that, where it's red in an acid, blue in a base.